In this section of the chapter, we'll talk about modern advancements in medical microbiology that have allowed us in the last 100 years to better understand the cause of and cures for infectious disease. One of the foundational advancements in the field of medical microbiology is the invention of the Petri dish. The Petri dish, in fact, allows us to do things like isolate microorganisms because it provides a solid surface on which the microbes can grow. Prior to this, microbes were only able to grow in test tubes or liquid culture, and purification and isolation was not possible. But once the same nutrients in liquid were mixed with a material or substance that turned that liquid into something that was semi-solid, we then have a very useful tool. Initially, the first time this was developed, the liquid was mixed with gelatin, essentially the same substance that we use to make Jell-O. Gelatin is produced from cow or beef hoof. And just like Jell-O, it's mostly solid, though a little soft. However, also just like Jell-O, if stored on a very hot summer day, the gelatin would occasionally begin to melt and soften. In addition, some bacteria have enzymes that can digest and eat their way through the gelatin, liquefying the semi-solid medium in the Petri dish. It wasn't until a female lab technician passed along information from the kitchen that helped the Petri dish become what it is today. This individual, Fanny Angelina Hess, suggested the use of seaweed instead of cow hoof as a solidifying agent. Seaweed contains agar, and agar, much like gelatin, starts off as a powder solid, which can then dissolve in liquid when boiled, and then when subsequently cooled again, can turn that into a semi-solid substance. Unlike gelatin, however, agar has a higher melting point, meaning it will remain solid for much warmer temperatures. In addition, microbes cannot digest their way through agar. So no matter what organism you grow on the Petri dish with agar, it will always contain and remain semi-solid, medium. This was then applied by Julius Richard Petrie, who used the idea of agar media and combined it with his Petri dish. Petri dishes are essentially spherical dishes that have lids that fit on top. The lids prevent additional contamination of microbes from the air to land on the surface of the agar medium, thereby allowing for cultures to remain pure and uncontaminated. The Petri dish is used daily in medical research labs. Another tool commonly used by modern microbiologists is a microbial stain known as the Gram stain. Hans Christian Gram, who lived roughly the same time as Julius Richard Petrie, Louis Pasteur, and Robert Koch, developed the Gram stain. The Gram stain is a type of stain that's known as a differential stain. Many scientists when they would like to view microbes under a microscope, must stain the microorganisms because microorganisms are often transparent and very difficult to see in a microscope. When stained with a dye, the microorganisms become more opaque and with the additional contrast readily visible. Hans Christian Graham wanted to develop a type of stain called a differential stain that would essentially stain different bacteria differently. In doing so, he generated a procedure that would first use a primary stain, crystal violet, followed by a fixative, which he used Lugol's solution and is now used in many labs as iodine, followed then by the third step of decolorization, which removes the crystal violet from some cells and not others. And then again in today's labs is followed by a second stain called a counter stain. The result of this is two different cell types based on their cellular structure. Some cells are stained purple and retain the crystal violet from the very first step of the Graham stain. These are referred to as Gram-positive cells. I remember that they are positive and they are purple because it both starts with P. The other option is the Gram-negative cell. Gram-negative cells are supposed to be red, though they often come out as pink. This is a very nice image of a red Gram-negative cell. Gram-negative cells are not able to retain the crystal violet from the first step, and so instead are stained by the counter stain, typically safranin today. As research in the field of medical microbiology became more advanced at the beginning of the 1900s, research turned from studying bacteria exclusively to even smaller microorganisms like viruses. Viruses were perplexing initially because they were not able to be viewed under a light microscope as a result of the fact that they are so small. However, there was evidence that they existed. One, viruses could be passed through a filter and cause an infection from one organism to another. They also showed evidence of leaving cell death wherever they existed. We can see this on petri dishes covered with bacteria. This is what's referred to as a lawn of bacteria. And on this lawn of bacteria, you can see tiny spots where viral particles have caused the death and destruction of the cells in that area. Viruses that infect bacteria are referred to as bacteriophage. Bacteriophage harm bacteria but cannot enter human cells. We'll talk more about why this is later. But what's good to know about bacteriophage is because they can target bacteria, and some human diseases are caused by bacterial infections, bacteriophage can be used to treat human infections. This is sort of like the enemy of my enemy is my friend. Some bacteriophage have in fact been recruited for this very purpose. And in lieu of using antibiotics, bacteriophage can sometimes be quite successful. Now, of course, if you were to get sick with a bacterial infection today, you're not likely to get bacteriophage treatment. You're likely prescribed a round of antibiotics. The first drug to treat bacterial infections was not officially an antibiotic, although sometimes today it's referred to as such. That first drug were sulfa drugs or sulfonamides, also sometimes referred to as triple sulfa drugs. These synthetic molecules are in fact a dye, not found in nature, but man-made. Sulfonamides have saved millions of lives and continue to save lives today. But most drugs people get today are antibiotics, officially named antibiotics because they are produced by one microorganism to kill another. Antibiotics have been around for millions to billions of years. They are the way that microorganisms fight each other in the soil, in the oceans, in nature. Humans discovered the existence of these drugs that microorganisms use to fight each other, and we now use them to our advantage. The very first time this was discovered was by Alexander Fleming when he discovered penicillin. Alexander Fleming was studying staphylococci, specifically Staphylococcus pneumonius, which causes a type of pneumonia. He had a bunch of Staphylococcus on plates and left for vacation, and when he came back, noticed that some of his plates had been contaminated. Many microbiologists would have just thrown these plates away. But Alexander Fleming took a closer look. And upon taking a closer look, he noticed that nowhere near the penicillium infection or contamination the staphylococci could grow. And he wondered if there was something produced by this mold, penicillium, a common mold that can grow on old oranges or bread, that would somehow inhibit the growth or even kill the staphylococci he was studying. This was important, of course, because as being a causal agent of pneumonia, he was looking for ways of killing Staphylococcus. It wasn't until subsequent years later, additional researchers in other labs were able to isolate the specific compound that Alexander Fleming initially discovered. In isolating the specific compound, they named it penicillin after the genus Penicillium, the name of the mold that forms it. Incidentally, your book has a small little mistake in the story of the first use of penicillin, and that was that the first individual in 1941 to use penicillin was not Robert Alexander, but Albert Alexander. It's not really a big deal, but I thought I'd bring it up in case you wanted to look up more information online. Interestingly, Albert Alexander was infected by staphylococci by simply gardening in his yard. He ended up getting a tiny cut in his face gardening, and that cut became infected with staphylococci bacteria. They tried to treat his infection with sulfonamides, but they didn't seem to help. And the infection ended up spreading all over his body and into his bloodstream. When this happens, the patient is at death's door. Scientists then tried putting penicillin into his bloodstream to see if that would subdue the staphylococcal infections. And while it helped temporarily, there wasn't enough to save his life. They even tried to isolate more of it from his urine as he was secreting superfluous amounts of it. But even then, it wasn't enough to save his life. More penicillin was clearly needed.